Namaste everyone. Welcome to wave optics class. In the previous class, we have seen the way of polarizing a light, right? What is polarization, how to represent a polarized light, and how the intensity decreases when you hold an analyzer in front of. Analyzer is like a polarized sheet itself, and the name is analyzer, that's all. So how do we get the light and all, right? So namaste. Ready for the class? Right. We have seen that polarization, very interesting phenomenon of light, and because of polarization we were able to conclude that light is also transverse wave in nature. And so if you incident an unpolarized light like this, if this is an unpolarized light which contains vibrations in all directions into a crystal or a Polaroid sheet, like tourmaline sheet, we get a tourmaline sheet, mica sheet, quartz crystal, and all those, they can do that. And you can artificially produce polarized sheet. That what is we are doing in cooling glass and all. Okay, suppose this is the pass axis, and only these vibrations are allowed to pass through, and other vibrations are cut off. You know this strictly. Now the thing is, okay, yeah, right. This is the polarized light, and this is the plane of polarization, and this is this is the plane of vibration. Sorry, this is the plane of polarization where no vibrations are present. Now, if such a light is polarized, and we can analyze it using an analyzer kept here, and if the pass axis of the analyzer is also parallel to the incident light, then you will get maximum light here, right? Maximum light here. And if the axis of the analyzer is perpendicular to this incident beam like this, then the intensity light will be minimum. Why it is so? Now the vibrations are not allowed to pass through this crystal, or they are completely blocked. But if you place this analyzer with its axis little bit turned like this, suppose the axis of this is not exactly perpendicular, say it at 60 degrees and 45 degrees, 30 degrees and so, then what is the intensity of light? It is neither maximum nor minimum. It is not very bright and very dark. Why it is so? Because this electric field, whatever I have shown, is not a single electric field. It is the resultant of many electric fields. Whenever you show light as a combination of electric and magnetic fields like this, what is this B and what is this E? That direction arrow mark is shown as the resultant of many magnetic fields. This is the resultant of many electric fields. For example, how much amount of light is here in the board in this region? If I ask you, the amount of light in this region is so much. But is it the light produced by only one source? No. It is the light produced by sunlight which is scattered and fallen here. It is the light produced by one bulb here. It is the light from one window. It may be the light from the LCD and all. All put together is the light here, right? So it is a combination of many lights. Similarly, this electric field, what I have shown in the diagrammatic representation, it is a resultant electric field of many other fields. That means this electric field is the combination of, it is a representation of many electric fields. That means where are the other electric fields then? They may be like this, like this, like this, like this, and all put together this came. Best example is, if you observe a small food particle moving like this at a certain distance, it is actually because many ants will be carrying the food particle together. Collectively they are doing work, right? Ants are supposed to be very hard workers but not intelligent, right? Suppose here is a food particle which is moving like this. From a distance you feel that this food particle is pulled by all the ants in this direction. If you think so, you are wrong. Some ants will be pulling the food particle like this, some ants will be pulling the food particle like this, and some may be even pulling it in the opposite direction, because they may not be knowing where is the target and where they have to push and pull. Some even may be climbing up the food particle and they will be enjoying. Actually, they are not enjoying. They are trying to push it, don't know where. So all these forces put together is this one. What is this force? This is the resultant force. Actually, what do we see from the distance is the resultant force. We see that the food particle is moving in a particular direction. But individually, all the ants will not be pulling that food particle in a particular direction. So this vector is not a single vector. All the ants strictly are not pulling the food particle in a particular direction as we pull a cart in a festival, right? In a festival, how the people will pull the cart? They will try a very big rope, thick rope, and they will start pulling it in the same direction, so that effectively it gets added up, so that effort needed is less. Whereas here, the ants are not so intelligent. They will be pulling in different directions and even in the opposite direction. Finally, the food particle will move like this. Actually, these opposite direction forces are of no use, and even the perpendicular direction force is a waste. So, the food particle will be carried somewhere else then finally. Okay, this is and can I call this as the resultant? And these are all components. What are components? Components are the set of vectors whose sum is the final vector. So, any vector is the resultant of many vectors, right? If a boat is moving in a sea in some direction, means it may be because of that resultant force is because of the weight of the ship, weight of the boat, and the force given by the sea waves, and the force given by the fishermen, everything added. Finally, we will get the resultant. Similarly, I have shown this electric field as like this, but that electric field is not a single electric field. It is the combination of many other electric fields. Electric fields may be like this, like this, like this, like this. But remember, whenever you get the component, suppose this is the food particle, and the food particle is finally moving in the resultant force like this. If the resultant has to be in this direction, then out of all the components, most of the components must be acting very close to this. Resultant is always in the direction of in the direction of the most of the forces. And whatever the forces which are acting in this direction must be weaker, otherwise the resultant would have been like this. So, in what direction most of the stronger forces exist, in that direction resultant force exists. That means you will never get any force like this. Or in short, in physics, if I want to say, if a main vector has to be split into component vectors, you can have components like this. You can never have a component like this, because a component existing like this will never will give you a resultant like this. All the components which are existing in this direction, in this direction, in this direction, all these put together can produce this resultant. But if there is a force like this, it will never give you a resultant like this. A vector can be split into many components. A vector may be the resultant of many components, and those components cannot be in perpendicular direction. We take components of vectors, right? Suppose this is a vector, and if this is x-axis and this is y-axis, we take the component of this vector A as, if this is theta, A cos theta, wherever is theta, and A sin theta, correct? We take it like this. Suppose this is A cos theta and this is A sin theta. Now try to get the component of this vector along the perpendicular direction to this. Not possible. What happens to A cos theta and A sin theta? So try to get the component of this vector along the perpendicular vector direction. A cos 90 becomes 0. A vector will never have its component in the perpendicular to it. What I try to explain here is very simple. Suppose this is the electric field which you have shown, like this, like this, like this. Sir, what are these electric fields? Let me explain it like this. And all these things are needed for your knowledge, not for the exam. As soon as I say that, don't shut your brain off, keep it switched on. If this is the electric field, what is this, sir? This is the representation of all the things, all the different electric fields. Then ask this electric field, you are the representative? Yes, sir. How many of you are following it? How many of the electric fields are following you then? Sir, there are many electric fields. There is an electric field like this, there is an electric field like this, there is an electric field. But there is no electric field in the perpendicular direction. Any vector cannot have component in the perpendicular direction, right? Best example I can give you that you can't have a component in the perpendicular direction. You find it difficult to walk upstairs, right? When you move upstairs, when you move totally like this, you feel tired. So when you move from here to here, you get tired. But you don't get tired when you walk on the ground. Why? Because when you move up through the stairs, you are going exactly against gravity. You are doing work against the gravity. You have some force which is opposing you. You have to do an extra work against that force and you have to do the job, right? Whereas when you are working like this, the gravity is like this and your motion is like this. This gravity has no component in this direction. So gravitational force has nothing to do with your direction of motion. So you need not have to worry about the gravity. You need not have to lift your body against the gravity. You are just moving on the same ground and gravity doesn't disturb you. So this gravitational force, its component along this direction is 0. Component of gravitational force along this direction is 0. It doesn't disturb you at all. Whereas component of the gravitational force exists in this direction. It is full gravitational force against which you have to do the work when you go upstairs. But when you are walking on the ground, gravitational force exactly acts vertically downwards and it doesn't disturb you at all because you are walking on the ground. You are not going against the gravity. So what is the work done? The force that is disturbing you, nothing. Component of the gravitational force along the horizontal direction is 0. It is very difficult to lift a very large sphere is given to you, say. Very difficult to lift the sphere, but very easy to roll it. If you want to lift a sphere, it is very difficult because you have to do the work against gravity. It is very easy to roll it like this. You can roll it easily because when you roll it, gravity pulls it down, but it has nothing to do in this direction. Gravitational force has nothing to do with your motion like this. So you can easily push it, no problem, because the component of the gravitational force doesn't act in this direction. It acts only like this, like this, like this, like this, but it no component in the parallel direction to the ground. Okay, if you still have doubts regarding this, you just ask me. You know the number, right? So, where we are now. So this electric field, which is a representation of many electric fields, will have its components. If you ask this electric field, it will say, sir, I am only the representative. I have to represent many electric fields, sir. Where are your, what you call, friends, right? Sir, there is an electric field here, there is an electric field, there is an electric field here, but no electric field in this direction. No component in the perpendicular direction. And the sum of all these pieces has made this electric field. There is an electric field like this, there is an electric field like this, there is an electric field like this, but no electric field like this and like this, not possible. And the sum of all these, vector sum of all these has given to this electric field. Now, when you turn the analyzer, I'll rub this again and again, I have to draw it. That's a headache, right? I will do it like this. I will take the duster and I'll show it. Now, when I turn the analyzer like this, like this, like this, what happens? When the analyzer is parallel to the electric field, the main electric field vector, most of the components were passing through it. Because if this is the resultant electric field, remember, almost all the components should be in this direction. Most of the components should be in the direction of resultant. So maximum amount of electric field components were passing through it. When I turn it, some of the components will pass through. When I turn it further, few components will pass through. When I hold the analyzer perpendicular to the direction of vibration of electric field, there are no components to pass through. intensity becomes 0. Got it now? So when I hold the analyzer parallel to the electric field vibrations, all the electric field lines were, all the electric field vibrations were passing through the crystal, I get maximum light. But as I turn it, only few components started passing through it, so they produce some intensity, lesser and lesser. But when the analyzer is exactly perpendicular to the electric field vibrations, what happens is no components were ready to pass. There were no components parallel to this electric field, so automatically the intensity of light becomes 0. So it is actually, this electric field is the representation of many components, and all those components should lie very close to the electric field, and no component lies perpendicular. Not possible. Suppose there is a component of this electric field here is existing, means this is not the resultant. Resultant should be somewhere else. You can't have that. Okay, that is about the intensity becomes maximum and minimum. And here I want to give you a law called Malus law. It is a very important law, and you must know how to apply it also. What is Malus law? He gave, Malus actually is, he gave a law, or he gave a formula to find out the intensity of light. He says that whenever an unpolarized light is incident on an analyzer, suppose you have a light like this, okay, which is unpolarized, contains vibrations, electric field vibrations in all directions like this, and if it is made to fall on an say polarizer, this is a polarizer and is made to hit here, this is the pass axis. Now what about the intensity here? Of course intensity reduces because we have lost many electric field vibrations, and electric field will contain only vibrations in a particular plane. He says that if I is the intensity of the incident light, then this intensity here I will write it as I naught, not I naught. Okay, I will take it as I naught. This is I by 2. Of course, this is not the law. So intensity of light coming out of any polarizer, any polarized light, after getting polarized, is reducing to half of the original intensity. So when unpolarized light is incident on any polarizer, the outcoming intensity will be 50% of the incident intensity. So I naught is I by 2. Now this law comes. How? If you hold an analyzer, now the question comes, how is the angle of the analyzer compared to these vibrations, theta? You might have hold this analyzer like this, right? You might have hold it like this way also. If it is held like this, then the vibrations are like this, and it is making an angle theta. Now what is the intensity of light? What is the intensity here? Depending on the angle theta. So if a polarized light is incident on an analyzer, then the intensity of the outcoming light depends on this angle. We know it, right? If it is exactly 90 degree, no light. And if it is parallel, maximum light. If it is at 30 degree, neither maximum nor minimum. So intensity of the light coming out of an analyzer inclined with its axis inclined at an angle theta is I is equal to, so I will call this as incident, and I will call this as incident by 2, right? Incident light of the unpolarized light, intensity of the unpolarized light. This is the intensity after coming out of polarizer, which is incident on the analyzer at some angle. The intensity of the outcoming light, that is what I call I. So intensity of the outcoming light out of the analyzer, I is equal to I naught, that is incident light, to the polarizer, not that incident light, this one, I naught cos squared theta. This is what is Malus law, right? Intensity, so see the situation properly. When unpolarized light is incident on any polarizer, outcoming light is I by 2, whatever be the angle. Here angle doesn't matter because this may be parallel to this vibration, right? This vibration. And when I turn it, it may be parallel to another vibration. When I turn it like this, this may be parallel to this vibration. No problem there. There is no question of angle at all. So when an unpolarized light is incident on an polarizer, the outcoming intensity will be half of the original intensity. Now comes Malus law. Whenever a polarized light is incident on an analyzer, which is inclined with its axis making an angle theta with the vibration, with the electric field vibration, the axis of the analyzer is making an angle theta, then the outcoming light's intensity is given by I is equal to I naught cos square theta, where I is the intensity of the light coming out of the analyzer, and I naught is the intensity of the incident polarized light, and this one incident polarized light, and theta is the angle between the axis of the analyzer and the electric field vibrations. Only electric field vibration which are remaining now, because it is a polarized light. So angle between the electric field vibrations and the axis of the analyzer, that is theta. Now you can apply it anywhere. You know that when the axes are parallel, okay, I'll rub this one. If the axis is parallel like this, what is theta? 0, right? That means same vibration should come out. Yes, cos 0, 1, I is equal to I naught. We got it? And when theta is 90, when you hold the analyzer perpendicular to the incoming light, theta is 90. What is cos 90? 0. Outcoming light, 0. Finish. And when it is 45 degrees, say, when you hold it at 45, it is neither maximum nor minimum. It should not be 0, it should not be the same intensity I. So what I can do? Same intensity I naught. It should not be same intensity I naught, neither I naught nor 0. So when I hold it at 45 degrees, cos 45 is 1 by root 2. Cos squared 45 is 1 by 2, half I naught by 2. It is 50% of the intensity. So when I reach to 45 degree, we get 50% of the light. When I go to 90 degrees, 0%. So this formula gives the intensity of light. So the statement itself is Malus law. The intensity of light, whenever, you can start it like this. Whenever a polarized light is incident on an analyzer, whose axis is making an angle of theta with the vibrations of the electric field, then the outcoming light of the analyzer is given by I is equal to I naught cos square theta. This itself is Malus law. Okay, that's very important law. Now in the entrance exam, suppose you are asked to answer a question like this. An unpolarized light of intensity I naught, but this is for polarized light of intensity I naught. If an unpolarized light of intensity I naught is incident on two crystals or two polarizers and analyzers, two crystal or two sheets which are inclined at 30 degrees like this, 30 degrees with each other. So I will incident unpolarized light on this. What is the intensity of light coming out? I naught is the light intensity, unpolarized light incident on the first crystal, and they are inclined at an angle 30 degree. What is the intensity of coming out light? Okay, that is simple. It makes like this. Okay, very simple. What I can do is, I have two crystals inclined at an angle 30 degree. So this is one, okay, and another one like this. Okay, compared to this axis, this one, this axis is at 30 degrees. Am I right? This one is the analyzer. It's confusing with too many lines. Yes, that is analyzer, and here is unpolarized light, like this, like this, like this, and here is unpolarized light of intensity I naught. It passes into this. Definitely it becomes I naught by 2, right, by the time it reaches here. But these vibrations are like this. Shall I use some other color so that it is yes, I don't know whether it is visible for you or not. So this is like this, this is like this. It hits the surface, and the inclined at an angle of 30 degree comes out. So what about the intensity here? If you want to know what is the intensity here is equal to incoming light I naught by 2. I is equal to I naught cos square theta. Here I naught itself is I naught by 2. From here onwards, Malus law. I naught by 2 cos squared 30. Okay, here this itself is I naught, I is equal to I naught cos squared theta, and this is 1. So this intensity is cos squared 30. So intensity of the outcoming light is I naught by 2 cos 30 is root 3 by 2, and it is 3 by 4. It is 3 by 8, correct? 3 by 8 of I naught. What is 3 by 8 of I naught? Intensity is equal to 0. 3 by 8 of I naught means 8 2 times 16, 4 remaining, 5. No. 8 3 times 24, 6 remaining, 7 times 8, something like this, I naught. Okay, if this is the answer, correct. 8 5s are 40, 4 remaining, 8 7s are 56, 60, 30, yeah. Now, suppose the question is like this. What is the intensity of light? It is 0.375 of I naught, that's all. What is the percentage of light coming out? Only 37.5%. Because I naught is 1 I naught, right? This is 1 I naught. What do you mean by 1 I naught? 1 I naught means 100% light. And after coming here, 50% light. 0.5 I naught. 0.5 I naught. After coming out, 0.375 I naught. 37.5%. So in percentage wise, if it is asked, you can do that. So that is Malus law statement and small problems, especially for entrance exams. But there may be a chance of asking for 2 marks also. We can't say, right? So that is about Malus law. And another thing is about production of these polarized light. How can you produce polarized light? There are different methods of producing polarized light. One is pass it through polarizer, any polarized sheet, pass it through analyzer, anything. That is possible. And another thing is polarization by scattering of light. Scattering of light produces polarized light. When light falls on atmosphere, it gets scattered, right? Because of the these air molecules, they scatter light in all the directions, and dust particles scatter light in all the directions, and there are many phenomena observed. So light coming into the atmosphere is unpolarized, and once it passes through the atmosphere, all the molecules, so if this is unpolarized light, so you know how to represent the unpolarized light. Once it is scattered in all the directions by the air molecules, suppose this is the polarized light, it contains vibrations in only one direction. This is polarized and this is unpolarized. Okay, so this is one method of producing polarized light. Scattering of light produces polarization. So you can do the polarization in your room itself. Take one beaker with the water, put some detergent or something, and put light on that. Then the light gets scattered everywhere, and that scattered light is polarized light. So polarization by scattering. Polarization by reflection and refraction. That is another phenomenon. This is very important. What is polarization by reflection and refraction? When a ray of light is incident on any surface, the reflected light is polarized and refracted light is also polarized. Whether they are completely polarized? No. That depends on how do you make the light to fall on it. Now, suppose a ray of light, so polarization by reflection and refraction. Okay, take a ray of light. This is unpolarized. So how to represent the unpolarized light? Dots as well as these vibrations. Of course, other vibrations I can't show. I can't show a crossed vibration like this. I can show only these two. This is unpolarized. So light is coming like this. Let it be incident at some angle. A part of the light gets reflected. A part of the light gets refracted. And this is the original direction. You know all these things. So when a ray of light is incident on any surface, a part of it gets reflected, a part of it gets refracted. Now both are polarized light. But if you find that at some angle of incidence I, The refracted light contains most of the vibrations like this, like this, like this, like this, in the plane of incidence. Where is the plane of incidence? It is the board, right? Where is the light incident? Light is in the board itself now. Light is not incident like this. Light is not incident like this. Not like this. It is in the board itself. It is not coming out of the board like this. So this is the plane of incidence. Where are the vibrations here? They are there in the board. But surprisingly, it is found that refracted light is not completely polarized. There may be few vibrations like this way also. It is not completely polarized, but most of the vibrations are like this. What about reflected light? Reflected light is this is polarized like this. That means it contains vibrations like this. Sir, don't you find out any any vibration, electric field in this direction? There may be some electric field like this way also possible. Sir, can I get complete vibrations only in this direction? You know what is this dot represents? Dot represents electric field vibrations like this, correct? Like this, perpendicular to the board. So don't I get vibrations like this? There may be. So how to get vibrations completely like this? No vibrations like this here also. What you have to do is try for different angles of incidence. So the story goes like this. When a ray of light is incident on a refracting medium, a part of the light enters into the medium, a part of the light gets reflected. Now, when the reflected light is polarized and its plane of vibration, most of the vibrations are perpendicular to the plane of incidence, and refracted light is polarized and most of the vibrations are in the plane of incidence, As you change the angle of incidence, when you reach a particular angle called polarizing angle or Brewster's angle, this is called Brewster's law. So I am trying to get Brewster's law. For a particular angle of incidence called Brewster's angle of incidence, you find that the reflected light is perfectly polarized. What do you mean by perfectly polarized? There are no electric fields in this direction. No electric field like this. No electric field like this. Right? No electric field like this. All the electric fields are restricted to this plane, like this, in the reflected light. Reflected light is completely polarized. Okay. Sir, what about refracted light? I can't say. It is not completely polarized. But it will be maximum polarized. What do you mean by that? This vibration may be missed out. This vibration may be missed out. Right? But this may be present. There may be one or two electric field lines like this. There may be few electric field lines like this. Okay, I will show one more here. There may be one or two electric, but most of the vibrations are like this. Electric field is restricted almost to this plane, but I can't say that electric field is existing only in this plane. There are electric fields like this. There are few. So there is a problem. So this is partially polarized. But partially polarized to the maximum extent. Other than this is not possible. Sir, can I try for more angle of incidence? No. If you still try for more other angle of incidence, this also is lost. Then you will get some vibrations here, everywhere. So this is the maximum amount of polarization possible in the refracted ray, and it is partially polarized. Okay, I'll complete. So now if I can recap the story. When a ray of light is incident on a transparent medium, a part of the light gets reflected, a part of the light gets refracted. If the incident light is unpolarized, then the reflected light is partially polarized, refracted light is also partially polarized, but as the angle of incidence is increased, for a particular angle of incidence called Brewster's angle or polarizing angle, Brewster's angle of incidence or polarizing angle of incidence. Some people use the symbol IP. That is also possible, right? So both are same because angle of incidence is equal to angle of reflection. So when the angle of incidence is increased, for a particular angle of incidence called Brewster's angle or polarizing angle, the reflected light is completely polarized and it contains vibrations only perpendicular to the plane of incidence. If the plane of incidence is the plane of the paper, vibrations in the reflected light, electric field vibrations are perpendicular to the plane of the board. Strictly, there are no vibrations like this way at all. So reflected light is completely polarized, but refracted light is partially polarized. It is not completely polarized. But the degree of polarization is highest. What do you mean by this? It has got polarized to the maximum extent, and beyond this you can't expect, even if you change the angle of incidence. So now at this condition, Brewster gave a law. He's a scientist. He gave a law. At this condition, he says that the reflected light and refracted light, this is the refracted light, right? They are perpendicular to each other. They should be perpendicular. That means this angle should be 90 degree. It should be 90 degree. That is what Brewster said. And of course, you can interpret it in another way. At the polarizing angle, the reflected ray and the refracted ray are perpendicular to each other. If these two are perpendicular to each other, what should be this? This is the angle of refraction, right? What should be this one? IB plus R must be equal to 90 degrees, isn't it? Because remaining in 90, because it should be 180. This is a normal drawn. So if this is normal drawn, this should be 180. And if this is 90, remaining this plus this should be 90. Totally it should be 180. So Brewster says that at the polarizing angle of incidence, the reflected and refracted rays are perpendicular to each other. One statement. Another way, tangent of the polarizing angle is equal to refractive index of the medium which reflects light. That is another statement. Tan of IB, if you get, you will get the refractive index of this medium. Remember, refractive index, ratio of the sine of the angle of incidence to the sine of angle of refraction, or V1 by V2 and all, right? So tangent of the Brewster's angle or polarizing angle must be equal to refractive index of the medium which reflects light. The medium which reflects light is this one. Its refractive index is given by tan IB. Now here you may get a 3-mark question. State Brewster's law and explain it and obtain the expression for Brewster's law. Now let us assume that IB plus R is 90 degrees, and then we will prove that it is true. Now how to do that? You have to draw a diagram, but remember, diagram should be very perfect. You can't have vibrations like this way here and dots here. Not possible. It is strictly restricted to the same one. That means reflected light always must contain vibrations perpendicular to the plane of incidence. And refracted light must always contain vibrations parallel to the plane of incidence. And there may be few vibrations here, but here strictly no other vibrations. So when a ray of light is incident at the Brewster's angle, the reflected light is completely polarized and refracted light is partially polarized, but degree of polarization is highest now. You can't have a polarizing polarized refracted ray better than this. Now at that moment, reflected ray and refracted ray are perpendicular to each other. Now tan IB is equal to N. How to get this? Shall I write this? Rub this? I'll rub this now. Here I will write it. Now tan IB is equal to N. How to prove it? Let us take this first. IB plus R is equal to 90 degrees. IB plus R. At the polarizing angle, the reflected ray and the refracted ray must be perpendicular to each other. We will take that part first. Okay. And we will apply Snell's law. You know, N1 sin I is equal to N2 sin R. You know it, right? Here this is R, say. 1 sin I is equal to N sin R. 1 sin IB is equal to N sin angle of refraction. This is the angle of refraction. 1 sin IB is equal to N sin R. What is IB here? IB is equal to 90 minus R. Right? So, what is sin 90 minus R here instead of IB is equal to N sin R. Okay. One minute. Yeah. Or shall I write it for, I want to retain IB, isn't it? Not R. So shall I write R, substitute for R, 90 minus IB. Yeah, that is better. Sin IB is equal to N sin 90 minus, because I want to prove that tan IB equal to N, polarizing angle. So R is equal to 90 minus IB. So substitute that, sin 90 minus IB. IB plus R is equal to 90 degree. Only 2 steps derivation. R is equal to 90 minus IB. So R is 90 minus IB. So what is this? Sin IB N cos IB. Correct? Sin 90 minus IB is cos IB. Put it here. What you will get? Sin IB by cos IB is equal to N. Tan IB is equal to N. Very simple. Very simple logic. So statement, explanation and small derivation. So what is Brewster's law? At the polarizing angle, tangent of the polarizing angle, tan IB, is always equal to the refractive index of the medium which is reflecting light. And all these stories, at the polarizing angle, reflected and refracted lights are perpendicular to each other. First story. Second story, reflected light is completely polarized and its vibration is perpendicular to the plane of the figure. And refracted light is partially polarized. Most of the vibrations are parallel to the figure. Correct? And this should be maintained always when you draw the diagram. This is very simple, at the same time very, very dangerous. If you go wrong here, you will lose much of the marks because they have weightage. Okay, so the things you have to remember here in the Brewster's law are, one is, if I can recap it like this, the things that you have to remember, one is this one, this is unpolarized light, like this, and a part of the light gets reflected, part of the light gets refracted, reflected light is completely polarized like this. This is Brewster's angle or polarizing angle. This is angle of reflection, same as this one, and this is angle of refraction, but here the vibrations are mostly restricted here, but very few vibrations here. There may be few vibrations like this. And N is equal to tan IB. One important equation, IB plus R is equal to 90 degrees. Another important equation you have to follow here. And another one is, if this is the original direction of the ray, if the medium was not present, the ray would have moved like this, right? The deviation of the ray from the original direction, because of the presence of medium, it has bent. This is called deviation. So how can you write the equation for deviation? Deviation is given by, see, this is straight line. This is straight line, correct? Original direction. This is IB. This is also IB. Am I right? This one. Opposite angles. Then what is D? Out of IB, you have to remove R. Then this is D. So IB minus R is equal to D. This is also very important equation. But we don't deal with this in this chapter because this is already has been done. So angle of deviation is total angle, which is opposite angle here, minus R. So these three equations play an important role while solving the problem, and Malus law. And that completes actually the that wave optics chapter itself. So we have completed 2 chapters, ray optics, wave optics. Wave optics is very, very important chapter as far as entrance exam, theory exam. But important parts in this case are that beta derivation, very, very important in interference. So keep practicing all these things. Shall we meet it in the next class? Hope you will read all these things together along with me. Just 40-45 minutes of class per day doesn't put pressure much more on you. And most of the teachers can't come to the college now for the reason that they can't come out, and more amount of cases outside. So I am trying to take the classes as far as possible and put it over. Try to read them, go along with us. Let us hope for the best in the future. Thanks for watching the class. Thank you.